today, first we're going to solve the quiz. Then I'll talk about some new material, which is not included in the exam this weekend. But we have to do it so that we actually have enough time in the remaining 3 weeks to cover all the subjects that we are supposed to cover in that weeks. Okay? And I'll try to finish as early as possible, and I'll remain in class. So if you have questions, you can come and talk to me before the recitation. All right? Good. So let's solve the quiz. Very quickly, I have charge Q on a ring of radius r, which is rotating. Each point on the ring is rotating with velocity v. So what is the first step is to calculate the current because of the motion of these charges. How did I define current? Definition of current was that it was the total charge that's passing through some plane in unit time. So all of the current in the ring, which is Q, would pass in one full rotation of the ring. So what would that be? The total length any point must travel is 2 pi r. And each point is moving with velocity v. So my current is qv over 2 pi r. Good. If now I have current I in this direction, can you tell me which way the magnetic field is? We had the right hand rule. How did we use that? We put our fingers, when I have a loop, along the current direction, and my thumb actually pointed to the magnetic field direction. So here I have rotation in this sense, so my thumb is pointing up. I can immediately say that magnetic field will have magnitude, and it will be along the z direction. All right? Good. So how do I calculate it? Well, can I use Ampere's law? Is there enough symmetry? No. So what do I need to use? I need to use Biot-Savart's law. And for that, let me look at the system from the top. From the top, if this is my x-axis and this is my y-axis, here is my ring. Now, I'll do the following. I'll say this angle is theta, and I'll take a small section with dl this way. The small section is seen by angle d theta. So dl magnitude will be just r times d theta. How about the direction dl cross r hat? Well, we've already said it will be in the z direction, but that's true not only for the full ring, but also for each small section. dl is tangent to my circle. R vector, what was the r vector? It was the vector from the current to the observation point, right? So it's r vector is like that. dl cross r is along z hat as we expected. So dl cross r will be dl magnitude, r magnitude. The angle between dl and r, if this is the r vector, is 90 degrees. So it's just going to be sine pi over 2, which is 1. R hat is a direction unit vector, so it has magnitude 1, and dl magnitude is r d theta, so that's great. So what's the small magnetic field created by this infinitesimal section? Mu 0 I over 4 pi. dl cross r hat is r d theta divided by r square. R's cancelled. Mu 0 I over 4 pi r times d theta. Magnetic field will be integral of these small parts all of these small magnetic fields are pointing in the same direction, so I can just do scalar integration without worrying about the magnetic field direction. So it's going to be mu 0 I over 4 pi r d theta. I start integrating at 0 angle and go all the way to 2 pi, which gives me mu 0 I over 2r. But I'm not done with my question, because I was not something that was actually given in the problem. It's something I actually calculated. So maybe I should use the same symbol overall. Let's do it like that. So I'll write qv over 2 pi r here. B is mu 0 qv over 2 pi r divided by 2r. So mu 0 qv over 4 pi r square will be my answer. How many of you obtained this answer? Could be better, right? Okay, well, good luck in the exam. We're way too close to say anything more, right? Now, let's talk about, unless there's a question, I'm going to start talking about our new chapter. But, okay, let's talk about induction. Now, we talked about how people discovered electricity, how they built batteries, more or less. And how did they discover magnetic field? Someone, his name was Ørsted, he noticed that if he has a wire that's carrying a current, a compass near that wire would change its direction. So he immediately realized that current creates a magnetic field. Okay, so current creates a magnetic field. But the magnetic field also applies a force on currents. Okay? So once this discovery was heard around Europe, people tried doing experiments with magnets and wires together. And one guy, his name was Faraday, he noticed something interesting. He said, hey, these are all good for static situations. So if nothing is moving, if the wire is constant, if the wire is carrying the same current, that's all good. But whenever I start changing magnetic field, something new happens. So here's what he did. He took a loop of wire and he took a magnet. Now, if both of them are static, there is no current in the loop. The magnet is not feeling any force. But once he actually moved the magnet towards the loop, he noticed something interesting. He noticed that there is a current running on the. Come on, I mean, that's really not acceptable. Okay. Now, he noticed that there is a current running in that loop, and the funny thing is, if you actually reverse the direction of the motion, again, a current, but this time in the other direction, flows in that loop. He did a lot of experiments. He tried doing the reverse. He kept the magnet constant and moved the loop. Said, okay, still there is the current. And then he experimented with the velocity that he's moving the loop with respect to the magnet. And the more velocity he gave to the magnet, the more current flowed. The current was stronger. All right. So he termed this induction. Okay. And it's actually quite magical, right? He is moving something without really touching a circuit. He is inducing currents. He is creating currents in that circuit. So basically what Faraday discovered is change of magnetic field can induce currents. But then he noticed something else. What happens? I mean, is the magnetic field really changing if I'm moving the loop? No, the magnetic field in space is constant. I'm actually moving the loop with respect to that. So it maybe it's not the change of magnetic field. Maybe we should be more specific about what's causing these currents. And he narrowed it down. He said change of magnetic flux through a loop will induce currents. Okay. So if I have a current loop, if I'm changing the magnetic flux through it, then I will actually see currents in that loop. Now, how did we define flux for any vector field? It was basically the surface integral. So let me do this definition more clearly now. I'm going to define magnetic flux much like I defined electric flux. It will be over any surface B dot dA. All right? So if I have a rectangular surface, my A vector can be defined like that. For a rectangular surface, if I have a constant magnetic field, the magnetic flux would be just B dot A. If I do it for small differential surface elements, it will be B dot dA. If I integrate it over any kind of curved surface, I would find the magnetic flux. Let's not go into the details of that, but what's the physical picture for this magnetic flux? What was our physical picture for electric flux in Gauss's law? We said it is the number of field lines passing through a surface, right? So you can think about this magnetic flux the same way. It's the number of magnetic field lines crossing a surface. All right? Good. Now, so here is where we stand. Okay. Faraday discovered that he has this loop magnet system, and their relative motion causes currents, induces currents. There is a great story. Faraday was doing these experiments in his lab. He was supported by the British crown, the royal, the queen, if you want. Okay. So one day, the finance minister came to visit Michael Faraday's lab. He said, you're getting so much money, let's see what you're actually doing. And he showed all these experiments about induction. The minister was not impressed. He said, okay, this is all very good, very nice. And so, what is it good for? And Michael Faraday said, Minister, don't worry, you will find a way to tax them. Tax them, okay? And it's actually quite interesting. Now, all of our electricity generation is done by induction. Okay. We are moving magnets against loops, we call this something else. We call it the generator. And here was the next important idea in induction. Faraday, Lenzs, all other guys, they were moving magnets with respect to these loops. One guy said, hey, if it's the change in flux, there's another way to change flux. Here I said it's B dot A, so this is B magnitude area times cosine of the angle between them, right? So what Faraday and Lenzs and other people were doing, they were trying to change either the magnetic field that's passing through the loop or the area of the loop some way. And one guy said, hey, what if I have this wire loop, if I rotate it under a constant magnetic field? So if I do my rotation, I will change the angle between the A vector and B vector, so my flux will change, and this is going to generate a current in my loop. Okay. When he told this idea to his supervisors, he was laughed at. Okay. But that was the basis of the generator and electric motors we all use today. Who had this idea? Do you know the guy's name who invented this idea of rotating the loop? His name was, yes, Tesla. Okay. And he should have become extremely rich, because this is actually a quite easy way to generate, as long as you have someone or something that's rotating your loop. You keep generating power, you keep generating alternating current in your system. Even the most advanced methods, okay, not the most advanced, but the most commonly used methods, like in a nuclear reactor. Do you know how nuclear reactors generate electricity? For a long time, I thought it was some, strange alchemical process. There is this nuclear decay and electrons go one way, maybe they collect it. Then when I learned actually how they do it, I was very disappointed. What they do is radioactivity creates a lot of heat, so they boil water, and steam actually drives the generators in a nuclear reactor. That's the most reliable way of generating electricity. In a hydroelectric dam, it's water falling from a height that's driving the turbines, that's driving the generators. In coal plants, you just burn coal, boil water, again steam is driving these generators. Only in a wind turbine, that's again the same thing. You have these propellers that are creating rotating the generator. Practically the only way of generating electricity without this induction is what we have in solar cells right now. Okay, and that's less than 1% of all electricity generated on Earth right now. Good. Now, so this was all very qualitative. The idea is that if I have a loop, and if somehow the magnetic flux through this loop changes in time, I get current. All right? Let's be more quantitative. First, let's try to determine the direction of the current in the loop. Okay. So, what is the direction of the current? Now, I think I'm going to tell you a statement which is called Lenzs Law. And as far as things that are called laws, I think this is one of the cheapest ones. Okay, you realize no one actually comes up with laws anymore. Have you heard about Einstein's law or Witten's law? Or no? We now have theories because we put them on mathematical foundations. In the 18th, 19th century, you went into a lab, you made an observation that's valid for, in different scenarios, 5 different scenarios. You came up with Lenz's law, right? So that's without the need for any mathematics. So Lenz's law is very easy to state. It says loops resist the rate, or I'm sorry, resist the change of flux through them. So they don't want the flux to change, so they create a current so as to make sure, so as to try to keep their flux constant. Right. For example, let's do this. Let's say that I have a loop here, and I'll get my magnet here, north, south. So the magnetic field is going into the loop. Now, so B is going into the loop. Now, if I move my magnet towards the loop, is B going to increase or decrease? B inside the loop. It's going to, B will increase because my magnet is coming closer to the loop. So the flux passing through the loop, is it going to increase? Obviously, the loop area is constant, so flux is going to increase. Now, Mr. Lenzs tells us that the loop doesn't like that. Okay, so the loop will try to resist, try to lower that flux. What does that mean? The magnetic field created by the loop, B loop, must oppose B external. So which way should the current of the loop be? Here, the external magnetic field is going into the loop and it's increasing, so the loop wants to create a magnetic field which is opposing this external magnetic field. So the loop should create a current which is rotating counterclockwise. Okay, so by right hand rule, I loop, so B loop is coming towards me, I loop is counterclockwise. Okay. That is pretty much, and it takes a few examples to go through this logic, but it's not very hard. Okay. Let's solve one example. The example is as follows. Let's say that I have okay, let's be more careful. I have an infinite wire carrying current I and a loop wire which is going away from the wire with velocity v. Find the direction of the current in the circular loop. Does everyone understand the situation? So I have an infinite wire. There is also a loop here. Now I'm moving this loop away from the wire. And I'm saying there will be an induced current, and I would like to determine the direction of this induced current. All right? Now, first of all, yes?
Does this loop has magnetic field around it, or is this a magnet?
No, it's not. It's just a loop of wire. So that's the nice thing. Okay, it's just a piece of copper wire. You put it onto itself, and somehow it becomes sensitive to how much magnetic field is going through it. So let's try to understand the mechanism. Why should there be a current in that loop? And it's not too hard. First of all, what's the function of the wire here? It's creating the magnetic field. Which way is the magnetic field created by this wire? I can find it by my right hand rule. Inside the loop, there is a magnetic field, the external magnetic field created by this wire, going into the screen, right? So there is a magnetic field going into the screen. But is the magnetic field larger or smaller closer to the wire? Obviously it's larger, right? So when I'm actually moving, so let's write this. B external is into the page. How about phi b? Is it increasing with time or decreasing in time? It's decreasing with time. Why? Because the magnetic field further away is less. So B is decreasing in time. What does Monsieur Lenz tell us? It tells us the loop will resist. The loop will try to keep flux constant. So B loop must be in the same direction as B external. Okay. So B loop is also into the page. If B loop is into the page, which way should the current flow? To create a magnetic field into the page, I must have clockwise current running through that loop. All right? I loop. Let's go through the logic again. That's good. It's not easy to understand. Now, there is a magnetic field going into this loop, right? But is the flux through the loop increasing or decreasing? Flux is decreasing. So the loop should create a magnetic field which is in the same direction as the external magnetic field. Okay? It doesn't want it to decrease. It wants to stop that decrease. Right? That's what Lenz said. That's somewhat of a cryptic statement. I really don't like this law. I don't think it should be called a law, right? And I think Monsieur Lenz is dead by many centuries right now, so no one is going to sue me. But right, so that's what he means by resist the change of flux. Okay, if it's increasing, it doesn't want it to increase. If it's decreasing, it doesn't want that decrease. Right? So let's go through this logic again. External magnetic field is into my loop. My flux is decreasing. So the loop creates a magnetic field which is in the same direction, which is supporting this external magnetic field, which gives me a current loop to create into the field must be clockwise. Right? Now, once I actually find the direction, let me be more quantitative. Let me actually try to quantify how much current will flow in such a circuit. And it actually turns out this is not too hard to do. So Faraday's law of induction tells me the following. If I have a loop which has magnetic flux phi b through it, but that changes in time, the change of flux d phi b dt acts as if some imaginary battery is tied to this loop. So induction acts like a battery in the loop that's driving the currents. So it actually creates, instead of calling this V for, again, historical reasons, it's called electromotive force, EMF. Okay. This epsilon is exactly d phi b dt, only just to remind us that there is this Lenz's law, there is opposition to the current, we put a minus sign here. Okay. So that is Faraday's law of induction. All right? d phi b dt, the change in flux with time, acts like a battery tied to my loop. Right? Which way the battery faces is determined by Lenz's law, and that's pretty much it. All right? Let's solve one example, and then I'm going to let you go. And here's an example. Let's say that I have a circuit with a resistor R that has linear dimension L1 here and no resistance anywhere. And here I put a metal bar that can slide without friction. Okay? No friction. Let's say that there is a magnetic field that's coming towards me, uniform magnetic field everywhere. And if I pull this piece of metal with velocity v, I would like to find the direction and magnitude of the current over the resistor. First of all, why is there a current? Why is there induction here? Now, where is my loop? My loop is clearly here. Is the magnetic field changing? No. Is the angle between the magnetic field and area vector changing? No. So area itself must be changing. Is it changing? Yes. When I actually move my rod to the right, I'm getting a larger area for my loop. Now, if the area is increasing, is the flux through my loop increasing? Yes. So the loop will resist, which means magnetic field created by the loop will be into the board. To create a magnetic field into the board, what should be the direction of the current? It should be clockwise. Okay? So this is quite nice. You see that we didn't even actually have to write these down. We know that current will be, the direction was easy, current is clockwise. How about the magnetic? How about the magnitude? Let's say that at some moment this length from the resistor to the rod is x of t. Can you tell me what's the flux through this loop? Well, it's b times the area of the loop. What's the area of the loop? L1 times x of t, right? It's a rectangle. So what's d phi b dt? B is a constant, L1 is a constant. It's dx of t dt. But what's this? Velocity, right? So it's going to be b times L1 times v. And that acts like a battery tied to my loop. So what's the current in the loop? It will be d phi b dt divided by the resistor. So it's going to be b times L times L1 times v times R. That's the answer I'm looking for. Sometimes people actually think of this as a general formula. If I have a piece of wire moving with velocity v, there is a voltage epsilon across its terminals, which is exactly B times L times V. All right. Now, this is all I actually want to talk about induction today. Good luck in your exam. I hope you'll do well. I'll see you next week.